Okay, so let me recall what we did on Tuesday. We were talking about total variation distance and couplings, and we'll keep doing that today with mixing times and more couplings. So let me recall. Our definition of the total variation distance between two probability measures was this. And this is defined to be the max over all subsets A of our state space X. So here mu and mu are two probability distributions on X. We're taking the max of the absolute value of mu of A minus mu of A. And we saw that this is also 1/2 of the sum over, instead of the subsets of X, just the elements of X, of the absolute value of mu of X minus mu of X. And we also saw that this is the minimum over some couplings. So we take the minimum of the probability that X does not equal Y, where this probability, the minimum is taken over all pairs XY that are couplings for mu and mu. So XY is a coupling of mu and mu. And I'll just remind you what a coupling is. So this is a pair of random variables. Okay, so a coupling of mu and mu is a pair x comma y of random variables such that well, first of all, the probability that capital X equals some little x is just mu of x, and similarly, the probability that capital Y equals some little y is mu of y. Okay, this is for all states x and y in our state space. Okay. And then we also had this definition, this notation d of t. So let me do this. Oh, I see. This is like, okay, whatever. Okay. So d of t. So t is some time. This is going to be the max over all little x in capital X of the total variation distance between p to the t of x dot and the stationary distribution pi. So the point here is that we have some Markov chain with transition matrix P. It's an irreducible finite state Markov chain. It has some stationary distribution pi. This is the probability distribution that's given by saying, like, what is the probability? So this is the probability distribution that assigns a probability to y, some element y, which is the probability of going from x to y in t steps of the Markov chain. So like if you start at x, what is the probability of being at y after t steps? And here, so this is two probability distributions. We take the total variation distance, and we want to maximize this over all possible x. So this is basically saying, like, how far off could we possibly be from the stationary distribution if we ran our Markov chain from t steps starting from some place. So the maximum is taking care of, like, how far off could we possibly be. And then we also have this d bar. Okay, so d bar of t was the maximum over all x and y in the state space x of the total variation distance between p to the t of x dot and p to the t of y dot. Okay. Okay, so now I want to define mixing time. So for some epsilon greater than 0, we're going to let t mix of epsilon be the minimum time t such that d of t is less than or equal to epsilon. So it's the first time at which this measure of how far you could possibly be away from the stationary distribution it's the first time for which that is less than or equal to epsilon. And we know that like as t is growing, this should be going to 0 because we're approaching the stationary distribution. So we're asking, what is the first time that it's less than or equal to epsilon? And it's also common to let just t mix without the epsilon. So this is the mixing time. It's common just to define this to be t mix of a fourth. The choice of a fourth is kind of arbitrary, but yeah, it works. I think you want it to be some number, I guess maybe less than a half, but yeah, it's difficult to just use a fourth. Okay. So now I want to talk more about couplings and how we can use them to understand mixing times. Okay, so a coupling of Markov chains so two Markov chains with the same transition matrix P, so with transition matrix P is, well, it's a process, it's the stochastic process where we have tuples xt, yt for t greater than or equal to 0, such that, well, we just want each of xt and yt to be Markov chains with transition matrix P. So xt, t at least 0, and yt, t at least 0 are Markov chains with transition matrix P. Okay, so earlier we were defining a coupling between two probability distributions, and now we're defining a coupling between these two Markov chains, which are really sort of copies of the same Markov chain. So they're using the same state or the same transition matrix, and now we're coupling them together. Okay. And maybe I'll do this. Okay, a Markovian coupling so this is going to be a special kind of coupling of these Markov chains. So a Markovian coupling of two Markov chains with transition matrix P is a process Again, it's going to be xt, yt, t at least 0, such that, or well, okay, actually, no, let me define it as a Markov chain. So I'll just say it's a Markov chain. With state space just the Cartesian product of x with itself. Okay, so the states are going to be these pairs. And we want it to be such that first of all, the probability that x sub t plus 1 equals some element x prime, given that xt equals x and yt equals y. Okay, so this should be equal to the transition probability in our original Markov chain, so p of x prime. And there's another condition, but let me explain this. Well, okay, the second condition is basically the same thing. The probability yt plus 1 equals some y prime, given that xt equals x and yt equals y, is the transition probability in the usual Markov chain from y to y prime. This is for all x prime, y prime in the state space. Okay, so we're just saying that you have this Markov chain whose states are pairs. If you're at some state where you have little x and little y, then the probability of next going to a state where the next x value is this x prime, well, it should only depend on this x. Like, you can kind of ignore this y and just look at the original transition probability of going from x to x prime. Yes?
What would a non-Markovian coupling be?
Yeah, that's a good point. So I'll have an example in a second. Yep. Okay, so this is the condition, and yeah, there's a similar condition here. So yeah, let me give an example of this. So example, let's just take x to be 0, 1. And I'm going to let my transition matrix P just be such that P of x, y is a half for all x and y. Okay, so like the transition, or the transition diagram for this Markov chain looks like we have a state 1, or state 0 and a state 1, and maybe I'll use a different color. The transition probabilities are, here we have a half, this is a half, this is a half, this is a half, okay? And what I want to do is let y sub t, for t at least 0, be just a Markov chain with transition matrix P. And I want to do this such that, so let me specify the starting distribution for y0. So I want to say that the probability that y0 equals 0 is a half, and also the probability that y0 is 1 is a half. Okay? So we have equal chance of starting at each one of the states, and then we just run this Markov chain. But now I want to let let's let x0 be 0, and I want to let x sub t be y sub t minus 1 for all t at least 1. So, right, we start off at 0, but then whatever we do for, like, wherever this goes next is just wherever y started, right? So this is kind of following in the footsteps of y, okay? And the point is that, well, okay, this we define to be a Markov chain with transition matrix P, but then this will also be a Markov chain with transition matrix P because, well, you just start at 0 and then you just follow along y, and because y was a Markov chain with this transition matrix, this will also be. Okay, but now, okay, so I'll say that then this pair xt yt, t at least 0, is a coupling of Markov chains with transition matrix P.
Wait, for it to be a coupling, it has to be the same matrix for both of them?
Yeah, I think probably you could define it more generally, but for here we're going to assume that it's the same matrix. Yeah, so we have this coupling, and that's just because, okay, where did we define it? All we want is that xt is a Markov chain with transition matrix P, yt is a Markov chain with transition matrix P, so that's fine. But it's not Markovian, so it is not Markovian because, well, okay, for example, so since if we look at the probability that, say, x sub t plus 1 equals state 0, given that xt equals 0 and yt equals 0. So if we assume that xt and yt are both 0, well then we actually know that xt plus 1, okay, because of this formula, xt plus 1 is the same as yt, so it's 0. So if yt is 0, xt plus 1 has to be 0, so this probability is 1. But 1 is not the, where did I write it? 1 is not the transition probability in our original transition matrix P, right, which is like P of 0, 0. Okay. Yes?
Are we assuming that xt comma yt is supported on the entire state space, or are we just taking choices of x and y such that we're not conditioning on an event with probability 0?
Wait, sorry, so,
Like,
where?
if you choose x and y such that that you're conditioning on an event of probability 0, do you just ignore those
Yeah,
cases? Or?
yeah, I think we can just ignore that. Right, I see what you're saying. I mean, so I guess probably in most of the settings that we'll consider, it will be supported on the whole thing. So maybe this isn't an issue. I guess maybe, yeah, let's ignore the events with probability 0.
But like for example, like xt comma xt, do we want that to be a Markovian coupling? Like it satisfies the rule.
Oh.
Except it is like if you choose x not equal to y, then it doesn't make any sense. But sorry, little x and little y. I'm saying big xt equals big yt.
Okay, so they're the same thing. And is that a Markovian coupling? So you're saying that, oh, I see. Okay, so then like, yeah, the event that xt equals little x and yt equals little y doesn't happen if x and y are different. Yeah, I think probably we could ignore that. I would think, yeah. I see, yeah, but I see what you mean. Okay, yeah, hopefully that's okay to just ignore the events of probability 0. Okay, so we're gonna typically assume that the couplings that we have are Markovian. I think maybe sometimes I'll just say coupling and it'll be assumed that it's Markovian. Okay, let me also define one other thing. So this is a term I made up because like there's this equation in the book that's like 5.2, and they keep referring back to equation 5.2, and I didn't want to, like, for lectures, refer to equation 5.2. So I'm going to give it a name, which is maybe a dumb name, but okay, we're going to say that a coupling, so say coupling xt yt for t at least 0 is sticky. Okay, so this is not a term that other people use, but it's sticky if we have that if xs equals ys for some s, then that implies that xt equals yt for all t at least s. So the point is it's sticky because like you have these sort of two copies of your Markov chain, and once they agree, so once they hit the same state, then they have to stay together, they have to stick together throughout the rest of the process. Okay, so I think sticky kind of makes sense, but yeah. But in the book, this is like 5.2.
And X and Y are Markov chains?
Yeah. So it's one of these coupling of Markov chains with transition matrix P. Yeah. Okay, so here's a theorem. Let xt yt for t at least 0 be a sticky coupling of Markov chains with transition matrix P. Okay, and I'm going to suppose that x0 is some little x, and y0 is some little y. And we're going to define what's called the coalescence time. So this is tau sub couple. This is going to be the minimum s such that xs equals ys. So it's the first time that these Markov chains coincide, and then we're assuming that after that point they continue to coincide because it's sticky. Okay, so this is, maybe I'll point out, this is called the coalescence time. Coalescence time. Okay, then the conclusion is that the total variation distance between p to the t of x dot and p to the t of y dot is less than or equal to the probability that this coalescence time, okay, I'm going to write the following. I'm going to write probability sub xy. This is supposed to indicate that it's probability under this assumption that I've started with x0 equals x and y0 equals y. So it'll just be convenient in what follows to have this notation, which is like denoting the dependence on the starting states. Okay, so the probability that tau couple is greater than T. Okay. And the proof is not bad. It's kind of straightforward. Oh, I should do this. There we go. Okay, so the proof. Since xt, yt is a coupling. Okay, so I want to say, not as a process, like I'm not drawing the subscript here. So just the pair for a fixed t, xt, comma yt, this is a coupling of probability distributions. So this is a coupling of p to the t of x dot, right? This is a probability distribution on my state space, and so it's a coupling of this and p to the t of y dot. Okay? So because this, we have that, well, the total variation distance between p to the x dot and p to the t of y dot is less than or equal to the probability that xt does not equal yt. This is by the fact that I wrote here at the beginning, saying like you can bound this by by this probability that your coupling is not equal. And what does it mean to say that xt does not equal yt? That's equivalent to saying that the coupling, the coalescence time is bigger than t. Maybe I want the xy dependence. Okay, let me give a corollary of this. Corollary is that our d of t is less than or equal to the max overall states x and y of the probability, depending on starting at x and y, of tau couple greater than t. Okay, so also, I'll just say, so the mixing time, which I defined here, T mix, is less than or equal to 4 times the max over x and y of the expected value. And I'm also going to use the xy subscript to denote the dependence on starting from x and y of the random variable tau coupling. Okay, so let me prove let me prove the corollary. So, okay, we can use Markov's inequality, okay, everything is named after Markov. Okay, so proof by Markov's inequality which I'll remind you what this is. We have that the probability, depending on x and y, of the random variable, the coalescence time being greater than t, is less than or equal to the it's less than or equal to, the expected value of tau couple divided by t. Okay, so in general, Markov's inequality says that if you have some random variable that takes non-negative values, like in this case it's the coalescence time, then the probability of your random variable being greater than some real number t, some positive real number t, is less than or equal to the expected value of the random variable divided by t. So I'm just like, that's exactly what this is saying here. Okay. Okay, well, if we take t to be greater than or equal to, greater than or equal to 4 times the max over x and y of the expected value, depending on the starting states x and y, of this tau couple, well then, we get that d of t. Okay, so this inequality actually just is following from this, right? Like, because d of t is like the maximum over states x and y of this. So here I'm just taking the maximum, that's fine. But then the point of what I want to prove is this inequality here. So d of t is it's less than or equal to the max over x and y of this probability that tau couple is greater than t, and that is less than or equal to the max over x and y of the expected value of the expected value of tau couple divided by t, but now I'm taking t to be greater than or equal to 4 times this maximum, so this is less than or equal to a fourth. And so the point is that, well, what was the mixing time? It was the smallest t for which d of t is less than or equal to a fourth. Here I'm saying that if t is greater than or equal to this number, then d of t is less than or equal to a fourth. So that's just saying that the mixing time is less than or equal to that number. Okay, yes?
Wait, I thought we were wanting d bar t to be that full variation of dt.
Oh, did I mix it up? Wait, sorry. Oh, you're right. This was d bar t. So where did I make a mistake? Oh, I see. It was, hold on. Yeah, you're right. Okay, we had a lemma that I had last time, sorry. So you're right, this should be a d bar. And there was a lemma that said that d of t is less than or equal to d bar of t. So then we just use that. Yeah, thank you. So this is now saying that d of t is less than or equal to a fourth. Okay, so, yeah. Yeah, maybe I'll fix that in my notes. Okay. Okay, let me do an example. We're gonna look at the lazy random walk on a hypercube. Example, lazy random walk on hypercube. So here I want to take the state space to be 0, 1 to the n. So I should say, okay, what is the hypercube? Well, it's a graph whose vertices are the elements of 0, 1 to the n. So each, there are 2 to the n vertices, and they're just the 0, 1 vectors of length n. And the edges in the graph are given by just flipping 1 bit. So we're going to do a random walk on this graph, except it's going to be lazy, which means that with some probability you have to stay still. So what we'll do is, at each step, choose a position, so like some position between 1 and n, uniformly at random. And we're going to flip that bit, well, with some probability. Okay, so we're going to choose this uniformly at random, and we will replace the bit in that position with a uniformly random bit. Okay, so what this has the effect of doing is saying, okay, I'm going to choose some position, maybe I choose like the 5th position, and I look at the bit there, which is either 0 or 1, and I just change it to either 0 or 1, just each one with probability half. So this has the effect of just staying still with probability half, because if there was a 1 in that position and I change it to a 1, then I didn't change anything. And then with probability half, we've moved along an edge of the hyperplane by flipping that bit. Okay. And we can couple 2 different copies of this Markov chain. We can couple 2 copies of this Markov chain. By just always choosing the same bit in each copy and changing it to the same thing. So by choosing the same position in each copy and changing it to the same bit. Okay, I think now it's working. Okay. I think that's good. Okay, sorry about that. Right, okay, so yeah, I was saying we have, this is our lazy random walk on the hypergraph, and then this is an example. And okay, so the point is that once these agree in some position, they'll continue to agree in that position.
Yes, they're the same.
Okay, so this becomes, okay, so maybe I'll say, once these chains agree in position I, they continue to agree in position I. So, what we want to understand is this coalescence time, which is the first time when they agree in all positions. And this is a standard coupon collecting problem. So, tau couple is given by a standard, or I guess the maximum of tau couple is given by a standard coupon collecting problem. So I'll go on, or I'll explain what this is. Collector problem. So we'll come back to the lazy random walk, but I want to talk about the coupon collector problem. Okay. Okay, so the setup here is there are n types of coupons. And at each time, we get a uniformly random coupon that we add to our collection, but this new coupon that we get could just be a copy of one of the old coupons that we already have, and our goal is to collect at least one of each of the coupons. So this could take a while because like maybe we get coupon 3 and then we get coupon 1, but then maybe we get another copy of coupon 3, then we get coupon 5, and then maybe we get another coupon 3. So we could just keep getting the same coupon many times. And the question is, well, how long does it take before we have a copy of every coupon? So we let tau be the time when we have collected all in coupons. And the proposition here is that the expected value of tau is just n times this harmonic number. So it's n times the sum from n equals 1 to n of 1 over m. Okay? So we can prove this. Well, I'm going to let tau k be the time when we first accumulated k different coupons. Let tau k be the time when the first time when we accumulate k coupons. Okay. K different coupons. well then, okay, I can just write tau. So tau is the same as tau n. It's the time when I first get all n of the coupons. And I can write this as a sum, which is tau 1 minus tau 0. So tau 0 is 0, right? Like at time 0, we have no coupons. So that's the first time at which we have none of the coupons. So tau 1 minus tau 0 plus tau 2 minus tau 1 plus tau 3 minus tau 2, and so on, up to tau n minus tau n minus 1. Okay. Now, tau k minus tau k minus 1, so one of these terms, is a geometric random variable with success probability n minus k plus 1 divided by n. So what this means is that, okay, a geometric random variable is where you have, say, a bunch of independent events. Let's say the success probability is p, so you have some event that succeeds with probability p and it fails with probability 1 minus p, and you want to know how many times do you have to do this before you get a success. So this is this random variable, which is keeping track of the number of times that you need to do it before a success. That is this geometric random variable. And in this case, right, that's exactly what we're doing, because if we have k minus 1 of the, like tau k, at time tau k minus 1, this is when we have k minus 1 of the coupons. And now, at each subsequent time, there are n minus k plus 1 coupons that we haven't collected. And so the probability of succeeding by collecting a new coupon that we don't already have is going to be this. And so we're looking at, like, this is the amount of time that we need to run, you know, to do this before we get the new coupon. So that's exactly this geometric random variable. And it's known that, so this is just a standard fact about geometric random variables, which is not hard. So the expected value of this random variable is just the reciprocal of the success probability. So that's n divided by n minus k plus 1. Okay, so then that means we can just use linearity of expectation and say that the expected value of tau is the sum, okay, it's because of this, it's the sum from k equals 1, or 0, right, 1, sum from k equals 1 to n of the expected value of tau k minus tau k minus 1. So that's just the sum from k equals 1 to n of n over n minus k plus 1. And then if I do a substitution where I let m equal, I think, n minus k, okay, so this just becomes n sum from m equals 1, or yeah, okay, it's n plus 1 minus k, whatever, of 1 over n. So this is the expected number of times that you need to wait until you get all the coupons. But then we also want to show something a little stronger, or something, yeah, better. Maybe I'll move this. So another proposition is for any positive real number c, if I take the probability that tau, this is the same tau from that proposition about coupon collecting, so the probability that tau is greater than in log n, this is the natural log, plus c n is less than or equal to e to the minus c. Okay, so the idea here is that the expected value is on the order of n log n, because the harmonic number here is roughly log n. And so we're trying to estimate what is the probability that it's bigger than n log n by some reasonable amount, which is the Cn, and the probability is, in some sense, exponentially small. Okay, so what's the proof of this? So maybe the heuristic way of thinking about this is you're expected to wait about n log n steps to get all the coupons, but you probably don't have to wait too much longer. Okay? It's unlikely that you'll have to wait a lot longer than that. Okay, so I'm going to let AI be the event that the ith type of coupon does not appear among the first n log n plus c n, maybe I'll do a ceiling just so that it's an integer, coupon draws. Coupon, like the first, this many times, so coupon draws. Okay, maybe, yeah. Okay, then, let me go to a different board. Then the probability that this tau is greater than ceiling of n log n plus cn okay, well this is just the probability that one of these events occurs. Right, so each one of these events is like the event that the ith coupon does not appear among the first however many coupon draws. So the probability that at this time you haven't collected all of them is just the same as saying that one of these events or more occurs. So it's the union from I equals 1 to n of a sub I. And that is less than or equal to the sum of the probabilities. Right, so in general, just the probability of a union of events is less than or equal to the sum of the probabilities of the events. And okay, what is the probability of a sub I? Well, the point is that at each step, at each time step, you have a 1 minus 1 over n chance of not getting coupon I. So this is going to be sum from I equals 1 to n. You have a 1 minus 1 over n chance of not getting coupon I in each step. And we're saying that has to happen in all of these ceiling of n log n plus cn steps. So that's just going to take this to the power of ceiling of n log n plus cn. Okay. And then, okay, you can do some standard inequality thing, and this ends up being less than or equal to n times e to the power of negative n log n plus Cn over n. So this is just some standard inequality. And then from this, okay, well I can divide here by n. Okay, so this is n x of negative log n minus c. And okay, well this simplifies to just, right, like the e to the negative log n is just 1 over n, so that cancels with this n, and we're left with e to the minus c. Okay. Okay, so so now we can go back to the lazy random walk on the hypercube. Which I'm erasing here. Okay, so when we did this coupling of the lazy random walk on the hypercube, this was really like a coupon collecting thing. If you look at like what is the maximum that tau couple can be, so okay, so in the lazy random walk on the hypercube, what we have is that this d, so we have this notation d of n log n plus cn is less than or equal to the probability that this tau coming from the coupon collecting problem is greater than n log n plus cn. And that's less than or equal to e to the minus c. Okay, so if we look at t mix of epsilon, which is again the minimum time at which d of t is less than or equal to epsilon, okay, well this should be less than or equal to n log n plus log of 1 over epsilon n, right, because, well, the point is that if t, wait, yeah, what do I want to say here? If I want this to be less than or equal to epsilon, then I want, well, that'll happen if this is less than or equal to epsilon, so I want e to the minus c to be less than or equal to epsilon, so that's saying that I want c to be, okay, well, let me just do this. I want e to the minus c to be less than or equal to epsilon, so I want minus c to be less than or equal to log of epsilon. Well, okay, so then that means c is greater than or equal to negative log epsilon, which is log of 1 over epsilon. And so the point is that if c is greater than or equal to log of 1 over epsilon, then we have that this is less than or equal to epsilon. So that means that the mixing time is less than or equal to n log n plus log of 1 over epsilon n. And I guess, okay, typically people just care about like what is the leading order of the mixing time. So in terms of the asymptotics, this is really just, well, it's O of n log n is the point. Okay. Like for a fixed epsilon, if epsilon is like a fourth, if this is just like a constant times n, and so what really matters is that it's like growing like n log n. Okay, I'm gonna do another example. I probably don't have time to go through the whole example, but I can start saying what it is. So here we're gonna do a random walk on a cycle. So, example, random walk on a cycle. So we're gonna fix a probability P between 0 and 1. Let's assume it's strictly between 0 and 1. And we'll also let Q be 1 minus P. Okay. And I want to consider a random walk on a cycle graph, but it won't be the simple random walk. So consider the random walk on an in cycle that at each step does one of the following things. It's going to stay still with probability 1/2. So this is giving some laziness that it has probability of staying still. It's going to move clockwise with probability P over 2. And then it'll move counterclockwise with probability Q over 2. And hold on. Okay, and our goal, so the thing that we'll show, is that the mixing time, so this T mix, which is like T mix of epsilon, where epsilon is a fourth, is between 1 over 32 n squared and n squared. So it's on the order of n squared, and we're going to get balance for what the constant out front is. Okay. Don't know if I have time. Yeah, I mean, I don't have much time, but okay, I can say something. Okay, so I'll start describing a coupling that we're going to use for the upper bound. Okay, so we'll construct a coupling which will be this xt, yt, t leaves 0 of two copies of this random walk started from some states x0 is little x and y0 is little y. Okay, So, okay, in the coupling, the particles are not going to move simultaneously, so that we won't have to worry about them like jumping over one another when they're one space apart. And so what's going to happen is that at each time, until they meet, so before we want them to sort of meet each other because we want to have this, we want to study this coalescence time. But before they meet, at each point in time, we're going to toss a fair coin, and then this will determine this will determine which of the two random walks we're going to move, right? So we don't want to move them at the same time. So we're going to toss a coin at each step to determine which one will move. And okay, I probably don't have, I have like 2 minutes, but at each time, toss a coin, a fair coin, to determine which random walker moves. Okay, but one nice property of this is that notice that we stay still with probability 1/2, so this will preserve that when we do this Markov chain, right? Like at each step, you have a 1/2 chance of not moving because you have a 1/2 chance of the coin not telling you to move. Okay. Okay, so then the point is that whichever one you picked is going to move clockwise with probability P and counterclockwise with probability Q. Okay, so this chosen walker moves moves clockwise with probability P, and counterclockwise with probability Q. Okay, so this is how we're going to couple them, doing this flip a coin and then one of them moves and then the other one doesn't. And I guess next time we can talk more about this coupling and analyze it.